Hi guys. So because of everything going on, I thought this would be a good alternative to lecture, where you'll see me just like writing down my notes and explaining the material to you like this. So it'll kind of be looking like we were in class and you're looking up at the projector instead of being physically in class. So I'm hoping this would help. So to start, I'm gonna start explaining section 3.4, which talks about concavity and the second derivative test. Now, the idea of concavity is very simple. It basically says that the graph of a function f can be analyzed by noticing certain characteristics about its derivatives. So, the concavity says that if a function f is differentiable on an open interval I, which means it can be differentiable, so it's a function you can find the derivative of. Yes. Now, the graph of this function is going to be concave up on the interval when f prime is increasing. That means the derivative, or the graph of the derivative, is going to be increasing, and is going to be concave down when f prime is decreasing. Now over here I drew like rough sketches of what a concave up or concave down would look like. And it's kind of pretty obvious. If it's concave up, it's going to be pointing upward. Concave down is going to be pointing downward. But another indicator you could use is if you try to pick random points on that graph and try to draw tangent lines to them. If it's concave up, every single tangent line you can technically draw is going to be below the function. Otherwise, it will intersect that function, right? And if it's concave down, every single tangent line is going to be above the function. Otherwise, it will intersect the function. Yes? So since this one is concave down, obviously f prime is going to be decreasing. And since that one's concave up, f prime is going to be increasing. Alright? Now, over here I have an example for you. We have f of x equals 1/3 times x cubed minus x. Now, the idea here is to find the open interval on which the graph f of x is concave upward or downward, and it could be both, as you can see from the graph, right? It could be both. But you need to find the interval on which f prime is increasing or decreasing. So as you can see here, I found f prime already. 1/3 times x cubed. So if I take this power right here, when you find the derivative, you multiply it in front, it becomes 3/3, right? Which is 1, they cancel. And the 3 minus 1 becomes a 2. And then over here you have an x. When you take the derivative of that x, the answer is obviously 1. Now, as you can see over here, the sign I have is positive. So this derivative over here, or this function, is a positive function when the parabola is pointing up because of it. Now, actually, when I drew it, I drew the line wrong. It's supposed to be like this. So ignore that one if you would. Because this point needs to be -1 since I have a shift to the bottom by 1. I'm shifting 1 down. Now this is my function. Now I want you to notice something. On the original graph of f of x, when we start at -infinity going all the way to 0, as you can see, we have the function where the slope here, or the incline, if you will, it's increasing slowly. It pauses and starts to decrease again up until I get to this point right here, right, which is 0. So from -infinity to 0, this function is obviously concave down, and any tangent line you can possibly draw is going to be above that function. And from this point onward is concave up, right? Now, you need to determine what those intervals are. So looking at the graph, you can easily tell from -infinity to 0, 0 to positive infinity, and those are the intervals where the function is going to be concave up or down. Now, from -infinity to 0 is going to be concave down, because 1, obviously the curve, you can see it. 2, because f prime, which is this graph right here, is going to be decreasing. Now, how can you tell that? Because it is possible for me to give you 2 graphs without the actual equation, or give you the 2 equation without the graph and ask you to be able to tell the difference. So over here, for x prime equals x squared minus 1. This is your x-axis, right? I'm asking you to ignore the line at the bottom, right? So if you notice, from negative infinity all the way to 0, which is this point right here, this interval, the x values are actually what? Sorry, the y values are actually what? They're decreasing, right? They're dropping in value, turned negative all the way to -1. So on this half of the function, which is the interval we're discussing, negative infinity all the way to 0, f prime is actually decreasing. Make sense? Which obviously matches the conclusion we have, that is concave down. Now, actually, here, let me just flip the page. So, if I graph that function again for you, real quick. Right? Now at 0 and at, I think it was half with +1, and doing this part. So this is the positive half of the function. I don't really care about the other half. Now on this side, we're going to look at the concave up. Again, with this, looking at this graph right here, and you can tell that f of x, which is 1/3 x cubed minus x, is going to be concave up on what? From 0 all the way to positive infinity. And on this interval, it's concave up because f prime of x, which is x squared minus 1, is increasing on that interval. It's increasing on the interval. If I show you the graph again, like that, so starting at 0 and it goes all the way up, the value is going to be increasing. So therefore f prime is increasing. So the idea of spotting it on a graph is very, very, very easy. Let me show you the theorem, because the concavity isn't always going to be presented to you in a graph form or in a function that you can graph easily, even if you use your calculator. So we have what we call a test for concavity theorem. Now, this theorem shows you how to use the second derivative of a function to determine the interval on which the graph is concave up or down. Because if you remember, at the beginning we said definition of concavity is what? Is that the graph of the function f is going to be concave up or down based on whether f prime is increasing or decreasing, right? Well, now I'm telling you that f double prime, so the second derivative, is actually going to give you a specific value. And the relation of this value to 0, whether it's less than or greater than, is going to tell you if this function is going to be concave up or down and determine the interval for you. So the theorem itself says, let f be a function whose second derivative exists on an open interval I. Yeah? Now, from this, there are two things you need to know about this test. Well, let me write the title. Test of concavity. I'm probably pronouncing it wrong. It's either concavity or concavity. I'm not sure which is it. So, but anyway. So, the first one is that if f double prime of x, which is the second derivative, is greater than 0, and what happens? And if it is less than 0, and what happens? So, double prime less than 0. Okay. So for the first one, if that value is actually greater than 0 for all x values in I, right? So for every single value on the interval we're considering, then that means that the graph is to be concave up. F is concave up. And if it's less than 0, then it's going to be concave down. So far so good. Now, let me get a new sheet. Alright, so let's see how that test works and how we could actually utilize it. Now, to apply this theorem, you need to locate the x values for which f double prime, or the second derivative, equals 0 or doesn't exist. Yeah? Because those are the answers you can actually find. If it's 0, here, f double prime of x, once it equals 0, or f double prime of x doesn't exist, which means the values where the function isn't differentiable, right? Because in trying to figure out what the interval is depends on these values. These values are going to be your cutoffs. So when it's 0, that's when you stop. If it doesn't exist, obviously you're going to have a gap. So once you identify these two, you can easily determine what the interval is, because it's basically going to be each space you have between those values. So let me show you an example here. So for this one, we have f of x equals 6 over x squared plus 3, right? This is my function. And the question is asking, determine the open interval on which the graph is concave up or down. Yeah? So first thing you need to know is that this function is obviously what? It's obviously continuous. How can I tell? It's because even though it's a rational function, you have x squared in the bottom, there is no value for x that will turn this bottom into 0, because that's what you worry about when you have rational functions. If you have 0 in the bottom, then the function is not going to exist. Therefore, you can't find the derivative. But since you have x squared, that means that no matter what x is going to be, it's going to be positive. So the only way you can turn the denominator to 0 is if you subtract a certain value from x that happens to be that same x. But again, we're adding a number. Therefore, the bottom is always going to be positive and always going to have an actual answer and never 0. Make sense? So even if x is 0 itself, you're adding a 3. So no problem. So the domain for this one is actually positive infinity all the way to negative infinity. Now, we need to start by finding the second derivative of this function. So I'm going to rewrite this in this form. 6 multiplied by x squared plus 3 to the negative 1 power. So all I did was grab the denominator and put it to the side of that 6. And since it was in the bottom, it gets a negative 1 power. Yes? So this is still f of x. Now let's try to find the derivatives. First one is the first derivative of x. And how do we find that? You need to take the derivative of the entire pair together, and then you take the derivative of the inside, right? So we start by 6 times the negative 1, which makes it negative 6, correct? Times the x squared plus 3. That remains the same. And now the power, negative 1 minus 1 becomes negative 2. Multiplied by. Now the derivative of the inside. You have x squared, which is 2x, and the 3 is a number, and the derivative of a number is always 0. So this is also multiplied times that. So this is my first derivative. Now let me find my second derivative. So to find the second derivative, I need to rewrite this a little bit to simplify it. So this is basically what? 12, negative 12x over x squared plus 3 squared. And it's in the bottom, so I get rid of that negative. Yeah? Alright. Now let's do the second derivative. So over here, we have a fraction, so I'm going to use the quotient rule. Derivative of the first times the second minus derivative of the second times the first over the bottom squared, right? So this gives you what? You have x squared plus 3 squared times the negative 12. So I derive the first one and multiply it by the bottom as is, minus, now the negative 12x remains the same, times the derivative of the bottom, which is going to be x squared plus 3 to the first power times 2x on the inside. Oh, I forgot the 2. There you go, times 2. And that's your numerator. Now the denominator is going to be x squared plus 3, which was squared, and once you square it again, it becomes to the power of 4. Yes? Now, to simplify, multiply all these together, you get what? 12x. Actually, you can factor this one out. One from here, they cancel with the bottom. So the bottom is actually x squared plus 3 to the third power, not the fourth. And so this one cancels, that one cancels. You get 2x, x squared, 24, 36. Yeah, 36. Minus, well, yeah, okay, so 36 times x squared minus 1. And this is my second derivative. So from here, I got to the point where I have an actual second derivative. Now I need to figure out if it's bigger than 0, less than 0, and I just need to solve it, yes? So, when f prime or f double prime of x equals 0, in order for this function to equal 0, that means the top has to equal to 0, right? Because if the bottom is 0, then it doesn't exist. If the top is 0, then that's what we're worried about. So let's find that. I'm just going to grab the top, which is 36 x squared minus 1, and set it equal to 0. Divide by 36, divide by 36. The 36 is going to disappear. You end up with 2x minus 1 equals 0. Moving the 1 to that side, and x is 1. Just 1. If you remember this, good for you. If you didn't, it's plus and minus. Plus and minus 1, because you have to take the root. So x ends up being what? Positive 1 and negative 1. And that is when f double prime, sorry, is actually 0. So that means that this function over here is defined on a specific set of intervals. So your interval is going to have how many cutoffs? 2, right? At the point negative 1 and at the point positive 1. So we start at negative infinity, go all the way to negative 1, and cut it, comma, negative 1 to 1, comma, 1 to positive infinity. You see that? See, this is why we need to find, at the beginning I told you, you need to find f0 or if the function doesn't exist. Because if you find those values, you're going to figure out where the cutoffs in the intervals are. After that, at every single time you encounter that value, just chop it. And obviously, since you cut it off, it's going to be at both ends, but that's how it works out. Yes? And again, the reason we don't have a doesn't exist here is because the denominator will never give you 0. So we're good. Alright? So this is the interval for this function. And just to clarify, this is the interval for f of x, not f double prime. F double prime just equals negative 1, positive 1. Alright. Let's continue. Now, from here, I want you to test it. So, here's my interval. I have these three values, right? Between negative infinity to 1, negative 1, negative 1, negative 1 to 1, and then 1 to positive infinity. So to figure it out, what you need to do is grab a test value between these. So we have from, okay, let me draw it as a number line. This might help. Here you go, that's a number line. At negative 1 and 1. This is 1, and this is negative 1, right? So over here, I need you to choose a value that falls between the negative 1 and 1. So let's go with negative 2, for example. We'll call this my test value. And between negative 1 and positive 1, I'm going to choose 0. And then 1 between 1 and positive infinity, and I'm going to choose 2. Yes? So now what you need to do is plug it into the second derivative. Because from this point, you need to plug in this value into the function we found to find out if it's actually going to be less than or greater than. Because what the finding the zeros served to do is basically give us how the interval is cut out, but you still need to figure out if the function is concave up or down. And this is how you do it. You plug in values within those interval into the second derivative. So I'm going to go up a little so you can see it. Here we go. This is your second derivative, right? 36 times x squared minus 1 over x squared plus 3, and then the whole thing to the third power. So I'm going to plug in. So if double prime of 2, I'm going to plug in 2 into this number and see what that equals. I'm going to plug in 0 into the second derivative and see what that equals. And then I'm going to plug in positive 2 into that number and see what that equals. Oh, over here is negative, by the way. I forgot the negative. Alright. Now you can do that too. If you have your calculators, please take them out and do it. Which I just realized I didn't take out my calculator. There we go. Alright. So I'm going to do it in front of you guys so you can, so maybe that would help. Let me see. Here's the fraction. 36 times, well, the x we're using this time, well, I'm going to use the 2 first. So 2 squared, is it minus 1, right? Yeah. Minus 1, the whole thing over. 2 squared plus 3, the whole thing cubed. Yes? The answer is, whatever that number is, it's basically greater than 0. It's a positive number. So, over here, if double prime of x is greater than 0. Oops, sorry. I was solving for this one. It's all over the place. Okay. So, just because I wrote that one down, let's do the negative one real quick. But again, it will be the same thing because once you square a negative, it turns out to be the same answer. So negative 2 squared is going to be the same as positive 2 squared. The number is going to be a positive result. And as for the 0, let's do that one pretty quick. 0 squared, that means this whole thing disappears because there's nothing to add. Yes, so it's basically going to be just 3 cubed. And over here is just going to be the negative 1 times this whole thing. So the denominator is not going to disappear, but obviously the numerator is going to be turned into a negative result, which is negative 36 over 3 cubed, and that will give you negative 4 over 3. So the f double prime of x function is going to be less than 0. So as you can see here, the fact that this one is greater than 0, that tells me that it's going to be concave up. Over here is going to be down, and then up again. Yeah? So again, finding the first derivative tells you if it's increasing and decreasing. So noticing if the function, if the first derivative is increasing or decreasing helps you tell if the function is concave up or down. But finding the second derivative, in that case, all you need to do is solve for 0, find the zeros, and find if there are any values where the function doesn't exist. And after those, you cut up the interval based on those, and you find if it's concave up or down. Now, while the first one seemed easier, but that's only because you had graphs, this one is the more useful one, and it's more direct and obviously algebraic. So the first derivative test helps you tell if the function is increasing and decreasing, which was section 3.3. In this one, concavity, you use the second derivative test because it's actually a lot smoother. Okay? Alright. So the function in example 1, as you saw, is continuous on the entire number line, which is why the whole thing went smoothly. Now, let me give you another example. And in this one, I'm going to try to show you guys what it means to have a point of inflection. Right? Actually, before I move the page, since it's a video, I just want to make sure you guys don't have to try and pause it real quick because I was moving too fast or something. So I'm just gonna allow you to take a screenshot. All you have to do is just pause it so you can copy. Yes. And then this one, second half. Hopefully this should help you out. All right. Here we go. Now, let's do point of inflection. Now, the idea of a point of inflection says that if the tangent line of the graph exists at such a point where the concavity changes, then that point is considered a point of inflection. So if you remember at the beginning when I showed you that graph of x cubed function where it did this, right? So we had a switch in the concavity, right? It was concave down and then concave up. So this right here, the point where they flipped, would be your point of inflection. See, the idea here is that the tangent line used to be on top and then it went to be on the bottom, right? Because you can't draw a concave line inside a curve, a tangent line inside the curve, because if you draw it here, it would actually intersect it. It has to be on top of it, to the outside. So tangent line on the outside, tangent line on the outside. So if the tangent line of the graph exists at such a point where the concavity changes, then the point of that, between these two concavities is actually the point of inflection. Now, there are three types of points of inflection. There are three types. One, where the tangent line is going to be diagonal, so it has a slope. Yes? So if, let me graph one for you. If the function looks like this, for example, right, where this is your point of inflection, and the tangent line looks like this, yeah, so it's kind of diagonal. And another one would be where the tangent line would have a graph that looks kind of like this. So if you want to draw a tangent line, it would be right around here, and it would be what? Horizontal, yes. And another one would be kind of like this, where the concavity is kind of sideways, like that. So the point of inflection right here would be a tangent line that is a kind of vertical. Well, you're not saying it. There. Kind of vertical. All of these are considered points of inflection. Now to be explicit, the definition of a point of inflection goes as follows. Point of inflection. Alright? So what is a point of inflection? A point of inflection is when you let a function f be a function that is continuous. Alright? So a function that is continuous on an open interval. On open interval I. Alright? And we let C, right, be a point in that interval. Yeah. Then, if the graph of if the graph of the function f has a tangent line at the point c f of c. So by this I mean the point that you have c, which is your x value inside that interval, and the value of the function at that point. Yes? So the point c f of c, then then this point is a point of inflection. Of the function f when the graph changes between concave up and down. So again, the idea here, a point of inflection is a point where the function changes its concavity from up to down, and it could be sideways too, but you're already going to see those examples, so don't really worry about them too much. Now, how do we use this point? Well, why is it useful? Well, the idea of a point of inflection is introduced because we have a theorem that can help you find this point of inflection, which is a tool you will use to analyze functions later on, right? So on the test, you could get a question that says, okay, I give you a function f of x. This is its graph. Analyze it for me. Tell me how many points is it? How many points of inflection do you have? How many minimums do you have? How many maximums do you have? Where is it increasing? Where is it decreasing? Where is it concave up, concave down? And the only thing I'm going to give you would actually be just f of x, right? So unless you're planning to graph it and go through all that work, this is actually a lot easier. So the theorem says, theorem 3.8, points of inflection. Theorem says, if the point c f of c, right? So the point of your point of inflection, the coordinates of the point of inflection. So I'm saying if this is point of inflection of the graph, right? Then either f double prime of x, of c, f double prime of c equals 0, or f double prime of c doesn't exist. Right? Which kind of takes us to the previous example we did. Do you remember after we found the points where f double prime equals 0 and we found it to be 1 and -1? So from that, you could have easily seen in the graph of the function the fact that those two values, they would have been the points where the function went from concave up to concave down to concave up again. So this is what this is saying. The point of inflection is where the concavity switches between up and down, and the way to find that point is basically going to be the point where f double prime is actually going to equal 0 or doesn't exist, which is your cutoff. Yes, so finding the point of inflection means you find your cutoffs, which is what we did, and then you find how the function behaves after you analyze the value of f double prime. Okay. So let me give you another example, and we will use the point of inflection theorem. Okay, so in this one, the question says, determine the point of inflection and discuss the concavity of the graph. So I don't need you to graph it for me, just tell me it's up, down, and describe it. So the function we're playing with this time is f of x equals x to the 4th minus 4x cubed. Alright? Now, first thing we need to do, find the second derivative. So let's do that. F prime of x is what? 4 times x to the 3rd minus 12 times x to the 2nd. Right? That was easy. Okay. F double prime of x. Again, 3 times 4 is 12 x to the 2nd minus 2 times 12 is 24x. Right? Now, just to make things a little easier to see, I'm going to rewrite this as 12x times x minus 2. I just factor 12x out. Alright, so this is my second derivative. These two are correct. Now, from this point, I need to figure out where this function equals 0, right? Which is why I wrote it like this. This way, I already factored it. It's already ready. If I set f of x, f of double prime of x to equal 0, then you basically get x squared, 12x times x minus 2 equals 0. So when you factor this, you have two choices, either 12x equals 0 or x minus 2 equals 0, which means x is either 0 or positive 2. Those are the two values where your interval has to be cut off. So I want you to draw a number line. The book says table, but I find this to be a little easier. Besides, you can technically make the number line to look like a table. So it goes from negative infinity to positive infinity. And my cutoffs is 0 and 2, right? So this is how it looks. Now, between these two values, you need to choose a number that falls on this line. So I go with negative 1. That's the easiest one. Between 0 and 2, I'm going to go with positive 1. And between 2 and positive infinity, I'm going to go with positive 3. So these are my test values. So after you choose your test values, I want you to plug them into f double prime of x and see how it behaves. Alright, so over here, we need to find f double prime of negative 1. And I need you to tell me, not the answer, I don't care about the answer, just figure out if it's going to be positive or negative. And you can probably tell just by looking at the equation. I mean, if we have what? We have what? 12x squared minus 24x, right? So if it's 1, squaring it goes away, you end up with 12 minus 24. The first one is obviously less than, right? Now the second one over here, you have what? You have f of positive 1, and if I plug this one in, it becomes also less than. And over here, oh wait, how can both of them be less than? Did I make a mistake on one of these? I think it's this one. Negative went away, but the negative over here didn't, and it was subtraction, so it turns positive. Okay, there we go, we caught it. It's actually greater than. Okay, so this one is greater than 0, less than 0, and now 3 When I plug it in, it becomes 9. That makes it greater than double prime, greater than 0. So the function goes concave up, concave down, concave up, because the second derivative value is bigger than 0, less than 0, bigger than 0. So over here is up, down, and up. And there, we answered the question. So all you had to do was find the second derivative, pick your points of inflection, solve for them, and then set them on the number line and plug them into the function for each interval. So again, I chose a value within the interval. I didn't choose the actual answers we got. Yes, and then you find out if f of x is concave up or down. Simple as that. Now, in addition to testing the concavity for the second derivative, the second derivative can also perform a simple test for the relative maxima and minima, which we mentioned in a previous section if you remember. So this test is based on the fact that the graph of a function f is concave upward on an interval containing c, and that f prime of c equals 0, then f of c must be a relative minimum of f. Yes? So, similarly, the idea of the second derivative is that if the graph of a function f is concave down on an interval containing c, then f prime of c equals 0. That means that fc must be a relative maximum on the function. Yeah. So if I want to graph it for you, rough sketch. Here's a function that's concave up, right? So since it's concave up, let's choose a value and call this one right here c. That means that f double prime of c is gonna be what? Greater than 0, correct? So basically I'm saying here that if f prime, so one derivative, yes, the first derivative, if prime of c equals 0, then, and f double prime of c is greater than 0, yeah, then f of c is a minimum. Yes, it's a relative minimum. Now it could be an absolute minimum, it just depends on the entire graph. But since we're talking about a segment right here, okay, this graph could continue to increase on this side and increase on that side, which makes this an absolute minimum. But it could also just concave down again, and then you'd end up with another minimum. So the idea here is that it gives you a relative minimum. Yeah. So again, concave up gives you a minimum, which makes sense because if the curve is up, the point has to be a minimum. And concave down is going to be a maximum. The point that looks like this. So if the graph does that, right, and if I choose this point and call it c, yes, and for this function, obviously f double prime of x is going to be less than 0 since it's concaving downward, and f prime of c equals 0, so it still equals 0. For both, the first derivative is 0, the second derivative is what switches, then f of c is going to be a maximum. Yeah? Now, let me give you the theorem of the second derivative test and what it means. Here you go. So, it's theorem 3.9. Second derivative test. Alright. So for this one we say let f be a function. Yes. such that f prime of c equals 0, and that the second derivative exists. So I'm not dictating what it is as long as it exists, yes? On an interval I containing C. So as long as there is a second derivative on an open interval that contains C, yes? So from this point you get what? Two cases. First one is if the second derivative itself is greater than 0. Well, I keep writing x, it's c. Second derivative of c is greater than 0, and if the second derivative of c is less than 0. So if it's greater than 0, then the function f, the original function, has a relative minimum at the point c f of c. And if it's less than 0, then f has a relative maximum at the point c f of c. Alright? Now, if the second derivative at the value c equals 0, so notice over here I said greater than or less than, and those are two cases I showed you, if it's concave up or down, right? But what if it actually equals 0? If it equals 0, then the test fails. Then this test isn't applicable, because again the function has to be continuous and it has to be differentiable. There's a lot of other rules that has to apply to a function before you can use a test on it. So it is possible for this test to fail, but this basically means that f may have a relative maximum or a relative minimum or neither, right? So if it's greater than, you get a minimum. If it's less than, you get a maximum. And if it's 0, it's neither. It's just you don't have it. But in such a case, you can use the first derivative test, and you can try to define characteristics that way to find out if it's concave up or down. Make sense? But yeah, a second derivative test doesn't always work if you get the case of f double prime equals 0. But I don't think you should encounter one of those, because those are like the extreme cases and they're very, very rare. Now, let me give you an example. Okay. So in this one, I want you to find the relative maxima for me, which means I want, a relative extrema for me, which means I want any extreme point, whether it's a minimum or a maximum. Make sense? And I said relative, so I don't care if it's absolute or not, just as long as it's a minimum or a maximum. And here's the function I want to test. F of x is negative 3 times x to the 5th power plus 5x to the 3rd. Alright? Now, let's begin by finding the first derivative. So f prime of x, and let me say, we have what, 5 times negative 3 is negative 15, right? X to the 4th, and then we have another 15, positive this time, and it's x to the 2nd. And just to make solving this easier on me, I'm gonna factor out 15 x squared out, and you end up with 1 minus x squared. And the reason I switched those two is because the x squared is negative, so I thought I might as well put it second. Now, if I take out a negative 1 as a common factor and then solve for it, over here, obviously, the first one is going to be 0. The second one over here, once you solve for this one, is going to give you negative and positive, positive 1. That looks funny. But anyway, so you have 0, negative 1, and positive 1 as your critical numbers. Yeah? Now, let's find the second derivative of this function. Again, I'm finding second derivative of this right here. So we have 4 times 15, that is what, 60, negative 60, times x to the third power, plus 2 times 15, that is 30, times just x, and I can factor out the 30 x out, and you end up with 1 minus 2x squared. So from this we saw that 1, f prime does exist, and we solved for 0, so we found f of c equals 0, right? So these are the c's where f of f prime equals 0. So that was the first step in the second derivative test. And then we found that the fact that the second derivative does exist, right? Okay. Now we need to apply the test. So the idea here is to find out if the second derivative is going to be greater than or less than, or neither. It could be neither. Okay. So now how many points do I have? I have 0, 1, and negative 1, right? Now I need to find out what those points are. So for this function, let's try it out. At f double prime of negative 1, because again it has to be at c. Yeah? So f double prime of c, if I plug this in, do you think it's going to be greater than or less than? Or maybe even equal to 0? Yeah? So at the point of negative 1 is going to be greater than. When I plug positive 1 into it, is going to be less than. So that means that between the point negative 1, the function is going to be concave up, but over here is concave down. But here's a problem. So over here we have a minima. Over here we have a maxima, right? This is a minimum, this is a maximum, because we have a point where it's bigger than 0 and less than 0. But that's not all the points we have. We have one more. It's the 0, right? I didn't plug in 0. If I try to find what 0 is, right, like this, it actually equals 0. So the rare case I spoke of is right here, in a polynomial. You see that? We got negative 1, plug it in, it gave me a relative minimum. Positive 1, plug it in, it gave me a relative maximum. So, all good so far. Now this one gave me a 0. That means that the test, what? Fails at this point, right? So because the second derivative test fails at the point 0, 0, you can use the first derivative and observe if the function increases for f on the left and the right side of the x equals 0 mark. Right? So let's do that. So if I use the first derivative, then you can see that the point 0, 0 is actually neither a minimum nor a maximum. Because again, it doesn't fall between greater than 0 or less than 0. It's exactly at 0. So even though the graph has a horizontal tangent at this point, let me graph it for you so you could see what I'm talking about. Again, this is a rough sketch. This is a point 0, 0, right? This is what, 2, this is 1, yeah, 2, right about here. So it does this, and then that. Yeah, I can't draw. And then it goes that way, and then that way. This is so this point right here is -1, -2. This right here is 1, 2, and this is 0, 0. So these are the 3 points we found. Again, look at the x values. It's 1, 0, and -1. So over here, as you can see, it's concaving upward. Therefore, at -1, as we saw, we have a minimum. At +1, it was less than, it was concaving downward, and we have a maximum. And at 0, we have what? A horizontal line. The tangent line right here is, even though it's a point of inflection, it doesn't exist. So you have neither a minimum nor a maximum because there are other points that exceed that point. Yeah? That's it. That's how you find the point of inflection. And use the second derivative test to figure out how to write down your minima and maxima of a function without actually having to graph it. Yes? So all you had to do was take the first derivative, find the points, solve for 0, and then take a second derivative, plug those points in, and tell me if it's greater than or less than. If it's greater than, it's a minimum. If it's less than, it's a maximum. And if it equals 0, then the test failed. Alright?